So we understand that elements with one valence electron per unit cell are metals because they have a half-filled band. This would be the alkali metals on the left of the periodic table. That materials with full bands, so these tend to be compounds, and a large gap to the next available band are insulators. Semiconductors are materials like insulators, but where the gap is on the order of kT. The canonical semiconductor silicon actually has rather a large band gap, but it's doped either with elements to the right of it in the periodic table that will donate electrons to an empty band, so the carriers are electrons, and this is N-type silicon, or take electrons from a full band, leaving holes as the carriers in silicon, and this is P-type silicon. This does not explain why the majority of the periodic table, so all the elements in columns 2 through 13, and many of the others in groups 14 through 16, are in fact metals. Most of these have 2 valence electrons, and so they should have full bands. What's going on? The answer lies in 3 dimensions. For a free electron gas, we know that all the k-states simply fill up to give you a distribution of k-states in a space in which the coordinates are kx, ky, and kz of radius equal to the Fermi wave vector. So it's a sphere with volume 4/3 pi kf cubed. However, for a periodic crystal, the Brillouin zone, which represents the available k-states for an electron, has dimensions of 2 pi on A in each direction. So let's draw a little cube, and remember we are now in reciprocal space. So this is 2 pi over A for each of its sides. So this now has a volume in reciprocal space that is 2 pi over A cubed. So the density of k-states that accommodated, say, 2 electrons per unit cell for a free electron gas would have to occupy now in principle those same 2 electrons, but in a different geometry. So if we just set these 2 volumes equal to one another and solve for the value of kf for free electrons, we end up getting around about 1.24 pi over A. So if we start in the center of the Brillouin zone here and draw a vector outwards, it passes through the sides of the box, because the volume occupied by the sphere, although it's the same as the box, requires a larger radius than half of the side of a box. So how then are these states accommodated? Well, in fact, we know that when the wave vector touches a Brillouin zone boundary, a Bragg reflection occurs, and so this free electron sphere then gets shaped something like this at a Brillouin zone boundary. So let's draw it in 2 dimensions now, where we're hitting the Brillouin zone boundary and hitting it perpendicular because the group velocity is going to 0. And this must mean, therefore, that there has to be some extra volume outside the first Brillouin zone. So I'll just draw a little bit of free electron-like looking distribution of volume, once again in a 3-dimensional plot of the k-states. So we make it 3-dimensional, and we'd have one of these funny shapes here. This shape here is called the Fermi surface in the first Brillouin zone, and we see that the first Brillouin zone, which would correspond to 1 band, is full. This little piece left over here is called the second Brillouin zone, and it is not full. So what's happened is the 2 electrons per unit cell, because of the distortion of the shape from a sphere inside a periodic crystal, has filled up the band as it should have done, but it's not able to quite account for the two electrons, and so a second band is formed outside the first Brillouin zone, and this is only partly full. So that means there are certain directions in the crystal in which the states available for electrons correspond to partly full bands, and that is the reason why copper and most other metals in the periodic table conducts.